So it's my great pleasure to introduce Michael Herzog, who studied mathematics, biology, and philosophy in Erlangen, Tübingen, and MIT, and then did a PhD in biology. He did a postdoc in Caltech. He was in Bremen, where he did something like assistant professor, in his own words. Then he was a temporary professor in Osnabrück, just as I am a temporary professor here. And then he became a full professor at EPFL in Switzerland, where he was a very, very, very lucky man to have me as a PhD student. Take it away, Michael.
Okay, thank you very much. It's very kind to be here. It's actually more or less a home run because actually there's so many students from myself. There's Lynn, Lucas, Dario, and even Radek was a student when I was a professor. He was a student in the class. So I'm being from Switzerland, but today this is much less Christmas. This is no chocolate today. It's mainly spice, and it's getting to be really provocative. And to be really provocative, so Adrian asked me about it, I have even a prologue that basically puts everything in the reality that at least as I see it in neuroscience. So one of the classic ideas in neuroscience is, or the main goals is to link perception or cognition to the underlying neural mechanism. And a classic example is here. I think you're all familiar with illusions, isn't it? That's all psychology students. So you see the Ebbinghaus illusion here, and that's smaller than this. And of course, you know, they have the same size. So you're heavily deceived, or the same is true for the conjugate illusion. And in a study by Schwarzkopf, they showed that actually this illusion magnitude can nicely be mapped on the size of the primary visual cortex. So they put people in the scanner, they measured the size of the primary visual cortex, which is maybe a credit card-like thing, and then what they found is a negative correlation. So the surface area is here, and the illusion magnitude is here. You can see the larger your primary visual cortex is, the less you are deceived. And that's true for the Ebbinghaus illusion and for the Ponzi illusion. So that sounds like an explanation we all want to have. We're linking one variable of perception and cognition, in this case perception, to one variable in neuroscience. So this is a nice example of a X explains Y monofactorial explanation. Something we like, and in particular also high-rank journals like it. Actually, if you don't have an explanation like this, if you have an explanation like X explains Y on Mondays, and only if you add some barbitural, and only for females, and only if they have birthday on a Wednesday, then they're not going to take it. You need the X explains Y type of explanation. And because it's so beautiful, they actually published this in 4 high-rank journals, Nature Neuroscience, and twice in Nature Communications. So that's all good. Except so we tried to reproduce this, and it just horribly failed. And part of the study is Maya, and I think she was here for quite a while. She just left.
Yeah, she still is.
She's still here. Okay. And what you can see is, you know, here we got this negative slope, this inverse relationship between the V1 size and the illusion magnitude. We have the same plot here, and you can see our slopes are actually all positive. So if there's something going on, then the opposite is going on. So we thought, okay, let's send it to Nature Neuroscience and make sure that wrong results are not out there. You can imagine what happened. They got all desk rejected right away. And the typical stuff, you know, for the readership, you know, why should you tell something that something is wrong when you have published it? But anyway, that's not my point here today. So they're saying, oh, this is really not the type we want, because what they want is X explains why. And so I'm not going, okay, this is a clear case of the reproduction crisis, no question about this. And it comes from these misguiding or misleading reward structures. If you don't make it to nature, you're not going to get a position. So what do you do if you get some data and there's a little bit of an outlier? Okay, it's your choice. I'm not going to do nature bashing here. I'm not going to talk about the reproduction crisis. I'm talking about you. Because the problem is not in nature. The problem is in your heads. And the point is that you all believe in X explains Y as a good prototypical explanation. And what I'm going to show you that this is wrong. So there is a deeper problem, and we suffer from this. So that was the prologue, and we will come back to this in an epilogue later on. So this was the first spice type of thing. Now we come to the main talk. So I just added this for you as some bonus. Okay, but it's going to be provocative too. So big question is, do we really measure what we think we are measuring? And of course, I don't know what you believe, what you're measuring, but at least what I believed for a long time turned out to be wrong. So let's talk about something super principle. Let's talk about tests. For example, what we do as vision scientists, we like contrast, we like Gabors. In this Gabors, we measure contrast sensitivity. Usually in our experiments, we just use one test because we want to basically measure something, again, in the underlying neural structure, for example, about the receptive field sizes in primary visual cortex. You're all familiar with these things, right? So you want to basically find out something about the tumor, and then you do a lot of psychophysical experiments. And usually, as I said, we're using one test, and with this test, we try to make inferences about the underlying mechanisms. That's the idea. So there's an assumption that one test is sufficient because one mechanism or one factor is at work. So what we do is we present these Gabors at the target absent present task. So here the Gabor is present and you push a button, say, yeah, it's present. And in this case, you say it's absent and you push it absent present. What we do then next, actually everyone does it just a little bit differently with different stimuli. We can then, for example, change the orientation or we change the spatial frequency. And what we're going to find out is something like this. If we have a Gabor in this target present absent task, then we see that for a one cycle creating with a low spatial frequency, you're worse compared to when you have a 4 cycle predictor. And with this, we can, as I said, make some inferences. So why do we use this Gabor actually to find out about spatial frequencies? Because it delivers a highly significant result. So it seems to be the test is a good test. It measures what we want to measure. We can do a little bit differently. Not differently, we can do something in addition. We can be interested, for example, in various populations. For example, this is an older population, so in blue, that's the data I just showed you. You see this effect of spatial frequency, but you see if we add older participants in red, yeah, there is another main effect. That means if you get older, vision does not get better. That's not super surprising, but that's what this says. Again, it seems to be this is good test because it delivers a significant result, both in terms of spatial frequency and in terms of to discriminate between young and old. So why do we use only one test? So there's two assumptions here. One test, one factor, and significance is a good guide to choose a test. And there's a third assumption is, yeah, we can use one test for our research question because in principle, we could use other tests. Here I'm varying spatial frequency 2, for example, this is very low, that's high spatial frequency. The idea is, if we had used, instead of these Gabor stimuli, we had used these letter S type of stimuli, we had get the same results, just presenting this absent present. So the idea is that tests that measure the same construct should correlate with each other. Okay, so these are the assumptions. Once more, we use one test because we believe there's one mechanism. We believe we can use independent tests, or we can use whatever test we want, as long as a significant result, and that similar tests correlate with each other. And usually we just don't think about it by using tests. Just everything that delivers a significant result is a good test. Okay? I think that's what we all do. One implication is, of course, if you have two tests that should measure the same thing, like visual acuity or something about aging or whatever you're interested in, this test should correlate with other tests. Otherwise, this test would be useless. If you go to an eye doctor and she shows you the Snellen E, and then you go to another doctor and he shows you the Landau Cs, one says you get the glasses and the other one says, no, that's not what you want. They should come up with the same result. If not, these tests are useless. Do we agree on this? Okay, good. Then you agree on this, that vision science has a problem because tests don't correlate with each other. That's what we found in the last 10 years. Just to make this super clear, these tests are useless. Okay, let's show what we found. We came to this like the virgin to the child. It was totally unexpected. So what we did is we were just interested in a totally different question and thought about, okay, how do these tasks actually relate to each other? We thought there is a spatial mechanism, like what we all do. We think about spatial illusion, spatial tests, And we use them as the eye doctors use this Landau C's or the E's. So we thought, oh, there are all these spatial tests. For example, this is the Freiburg visual acuity test with Landau C's, which I just saw there's a Landau street here. And here you indicate where the direction of the gap. So here that would be to the east. This is a Vernier task, if they left or right. Here we mask the Vernier task, the Vernier comes first, and then the gradient comes, that makes it harder. And we had a large one, a small one. We had a bisection discrimination task where here you push a right button, here you push a left button. And these were our spatial tasks, and we thought, oh, we need a control. We should see what correlations are actually if something is totally unrelated. So we added this Gabor detection task, which I have just shown to you. So our results are here. So how to read this? So these are correlograms. And the tests are here and here. And on the diagonal, you find the tests we measured twice. In this case, for example, we have the Gabor test, and we measured it twice. And what you can see is we get a nice correlation. So each of these little dots or circles is a participant. And these are Z-scale things, it doesn't matter. But you can see if a participant does a test twice, the results are rather identical. So the test is a good test. It really measures things. If you use it twice, it delivers the same result for the same participant. These are R squares. It's not stellar values, but they're quite reliable. And you will see they're much larger than what we're going to run. So if you do it twice, the test is a good test. So let's look what happens when we do correlations between the tests. So this is our acuity test, and this is our Vernier test. This is an R square of 0. That means there's nothing. You cannot be even low. Yeah? It cannot be less uncorrelated. Okay, these are not super normally distributed, fine. But still, you see, there is almost nothing. And this is true. If we mask it, it's true for the bisection test too. So there's no correlation at all. These tests have nothing to do with each other.
Is each data point a subject?
Yeah, one of these little dots is a participant. Yeah, and the cloudisher or the roundish, there are, the less correlations there are. So an R square of 0 means really nothing. The surprising result is that the task that was supposed to be a controlled task that correlated negatively. I have no idea why this is the case, but that's something we found all over the place in subsequent experiments. So no correlation. And this is true for almost everything. The only meaningful correlation is here between the Vernier task and the bisection task. Why they correlate with each other, I don't know. But the message is these tests do not measure spatial vision. They measure something about spatial vision, but not the same thing. Next, spatial illusions. So the whole thing started actually a little bit when this study came out. I said, oh, if V1 size correlates with spatial illusion magnitudes, then all spatial illusions should basically correlate with each other, mediated by the common factor of the primary visual V1 size. So we said, okay, let's measure these illusions. So we got a couple of these illusions, like the Ebbinghaus they had, then we had the Müller-Lühr, we had the Ponsos they had, and the tilt illusion, and as a control, we had 2 brightness illusions. I think you're all familiar with this, right? Yes or no? Yeah. Okay, fine. And you can guess what happened. Actually, this was done by Lukas, who was here a long time ago. This reads a little bit differently. I'm sorry for this. So here are no individual data. What you see is the correlations between the tests. So what we did is, go back to this. So what we did is, you get, if you were a subject, you would see this type of display, and then with the mouse, you're adjusting the size that they two match in size, yeah? And the bias is then the measure for the illusion magnitude, okay? So we have the illusion magnitudes for all participants, and now we correlate them. I just show you the aggregate data. So if the correlation is low, close to 0, then this is pale colors. And in addition, they have this roundish shape. If there's a high correlation, you got a strong color like that, and you get an ellipse. And you can see if you do this twice, you're super consistent. And there are some participants who are strongly deceived by the illusion, and others are not. So this is very, very reliable. But then if you look at all the other illusions, like this is the Müller-Lühr, what was this? The simultaneous contrast, thank you. And the tilt. You see, there's no correlations. So these are super reliable tests. That means you can be strongly deceived in the Ebbinghaus and not deceived at all in the Ponzo. Or you can be strong in both or weak in both. There's absolutely nothing common to these illusions. So the notion of a spatial factor or spatial illusions is misleading from the very beginning. So we thought, oh, okay, we looked in a lot of statistical things. I come to this a little bit later. So what we thought about next is, maybe this is super specific. It's pictorial. Maybe it's just really this very super display. But that's not the case. So what we did next is we had many of these versions of these illusion, of the Ebbinghaus illusion. So this is a standard one. We changed the color. Here, this is with rectangles. If you like soccer, we got soccer balls. If you like tennis, we got tennis balls. We even rotated them and things like this. And what you can see right now is these are super strongly correlated with each other. So if you're strongly deceived by this, you're also strongly deceived if the flank contextual disk actually rotate. So it seems to be there is a factor. It's the Ebbinghaus factor. So each illusion actually makes up its own factor. But there is no factor behind. There is no latent construct behind these type of spatial illusions. That's a problem. Okay, next. So we thought, okay, that's problematic. And there must be somewhere something behind. We thought, okay, if we look at aging, we all know that people get, when they get older, things don't get better, I can tell you. For example, we know that you get the lens clouding, the optics get worse, all these type of stuff. And same is true in visual cortex and so on and so forth. So we thought the rationale is, okay, if we can't find this in the young population, we should at least find this in the old population, because someone who is legally blind must be bad in all tasks. Yeah, this is by definition, we don't need to measure this. Yeah, if you close your eyes and do the task, you're performing worse than someone who has eyes open. Yeah. So that what we did is we got 200 participants, old and youngs. These were around 70, 21. And we did what people usually do. We just tested them in tests that we can find usually in our conferences. And we had the masking task, we had the Gabors, we had some biomotion, normal motion, and visual search. It doesn't really matter. We just got a lot of tests, also some cognitive tests. So if you like cognition, they're here too. And what we found is what everyone else finds too, is that when you get older, things get worse, and that you can appreciate by looking at Y, which is young and old. This is biomotion. You see there's a huge difference. But you can see this is super large. We get p-values that are at 0. Usually, that's the reason to open a bottle of champagne, but there's no reason for champagne. It just tells you that when you get older, things don't get better. So that's basically what we find in accordance with what everyone else has found. The only difference is that usually people, when they investigate these type of things, just focus on one test because they believe that's representative for aging because they found a significant result. So what they do is they take the verniers or the motion task, and then they spend the rest of their life finding out what's wrong or what's getting older in the older people. That's usually how science is. And you do a little bit of genetics, put people in a scanner, yeah, whatever you do. The only difference is that we measured this in the very same participants. So this is basically, if you collect it from literature, you get exactly this, but we have the same data from the same people. And what you can see, there is huge variance in the older population. Yeah? You see that the standard deviations are much larger. So we expected that someone who's bad, say, with the biomotion or something like this, will be bad with in another task too, for the simple reason, because maybe there is some deficits behind this. You can guess what's coming out. This is the young participant. Sorry, this is another type of to plot the data and should come up with one format. I'm always saying this in the talk and say next time it will happen, but it will never happen. So anyway, this is individual data. This is basically a color plot again. So pale colors means no correlation. And I'm not going to guide you through this because you have seen how these correlate feed. What you can see is this is all pale. So these tasks simply don't correlate with each other. Even so, we have 200 subjects. You can quantify this a little bit if you want. A coinc d, r square smaller than 0.1 usually counts as negligible. So if you do a correlation and your coinc d is below 0.1, usually that means forget it. So we did this. We have 192 pairwise comparisons, and 157 out of these ones turned out to be smaller than out of 1. Again, this is a reproduction what we had before in the normal healthy controls. So now we're switching, this is young, now we're switching to old, and what you can see is things get even paler. They're all white, except for a few test-retest situations. So if you quantify this, 175, that means 15. Except for 15, there is nothing. And out of these 15, actually 7 are test-retest. So there are only 8 meaningful correlations. And this is not corrected for multiple comparisons. If you do this, you're ending up with nothing. So when you get older, actually the correlations go down, which means actually we become more individual when we get older and not less. So actually age decreases correlations. That means when we get older, we see the world more differently than when we are young. Actually, we looked into kids right now. Even from the beginning, there's not so much. Okay, even here, there is nothing. So you might say, oh, this is all about correlations, and correlations are just pairwise comparisons. This is all true. I don't want to bore you with what we did. I think we tried everything we could imagine, isn't it? And nothing worked. So we did PCA, we did whatever, factor analysis, and. There is nothing. Okay, so I told this to eye doctors, and they smiled and say, oh, nice try. I told them your measures are useless. There is one little thing to say. They're both right. They're right and yeah. And I said, no, listen to this. So they said, oh, look at our studies. And I said, I did this before. I'm not stupid. And this is a typical plot. The logarithmic plot is a little bit complicated, but that doesn't really matter. So this is a classic one where they basically try to standardize eye tests. And what you can see is here actually the larger the value, the worse it is. And indeed, there seems to be a nice correlation. And I said, yeah, I saw this nice correlation. But this nice correlation contains people who are legally blind. Sure, if you include legally blind people, you need to find these correlations. I'm just talking about the 95% of the healthy population, which is these ones. And these causes are the healthy population. These are the 95% of the normal people. And if you correlate these ones, there is nothing. They went back to their data, and of course, I don't need to go back to the data, you see it, but they went back to the data and it just came out, yeah, there is no correlation. So these tests are good to find out if you can discriminate between 2 and 5 fingers, but they cannot make any educated guess about the normal healthy population, particularly for the tests we standardly using in the normal student population in our labs. So we looked into, we said this cannot be true. There must be something wrong. So we went into the literature, and it just turned out, usually literature is usually super mixed, it just turned out no. Everyone agrees on this, even those who got different conclusions. If you just recompute the data properly, just turns out there is nothing in the data. In all studies we checked, that was super surprising. Okay, last thing here. So we said, this cannot be true. You know, isn't it that some people have better vision than others? Do you really believe this is more, we are more or less average, one is a little bit good here and here? There seem to be people who are super good, isn't it? And others are not. And actually it turns out it's true. There is something surprising here. And the point is that intuitively we underestimate variance. And I'm trying to make this point right now. If you want, you can just sleep a bit. And otherwise, let's see how it works. So what we did is we took all the tests and simulated a null result. So for each test, we randomly assigned ranks to virtual observers. So if you were the virtual observers, Adrian is number 1, he's always number 1. So he's number 1 in this test. And then you will be number 2, and you will be number 6, and so on and so forth. And then we do this for the next test. Again, randomly assigning ranks, yeah, how good you are in class. So this time, no, you will be number 10. And someone will be last. And so we do this all over the place. And so we can simulate this with a Monte Carlo simulation and see how these ranks actually, sorry, forget this. No, forget it. So what we did first is we did this with real observers. So with real Adrian, we did this, you get number 1 in this test and you number 10 in this test. So we computing the real ranks for everyone. And the virtual observers, we do a next step, sorry. Yeah, once more. First, real rank analysis for all of you. So what we can do then is, this is here. So here is the mean rank, and here is the participants already ordered by their mean ranks. So the best one is here. In blue, we have the young ones, and you can see the best participant here has a mean rank of 40. That's rather good, yeah? It means, you know, I don't know, I think it's 20 tests and 20 tests. I mean, it's maybe always number 2, then you're super good here. So this is super good. No, it's not entirely good. Anyway, super good subject. There's a super bad subject here with a rank of 140. So there are people who are good and those who are really bad. And it mimics what we have expected, that the young ones are good and the old ones are bad. This is really strange. How can that happen? And now comes virtual observers. Now what we did is we said, oh, let's run a null model. And what we did is we basically, instead of having you, we have now the same number of virtual observers, and we just said, oh, there's absolutely no correlation. In each test, we just randomly assigning ranks. What you can see is right now is these triangles here come out of these simulations. That means, yeah, there are super good people. And there are super bad ones, but not because of a common factor. It's not because there is a gain and, you know, some are low in gain and others are good. It is just a lottery. It's a random lottery, and these are the lucky winners, and these are more the unhappy ones. So it is just by randomly assigning a rank to you that basically explains this high variance in the data. And I think the same is true for talent. So I have absolutely no ideas about talent, but you know, Einstein believed he had this extra low, or there's this Mozart gene. I think there's no Mozart gene. I think there are maybe thousands of Mozart genes, and Mozart was just the happy one for the job he had, and Einstein the same. But that's potentially how it is. But anyway, okay, so much to this. Last thing, schizophrenia, studied by Dario. Very quick. So we had 120 patients and 74 controls. We did resting state EEG. So the patients and controls came in, they closed their eyes. We recorded EEG for 5 minutes with 64 channels. And usually then you look for one EEG measure. So you're looking, for example, for the alpha band or the beta band or things like this, right? And then you have a story. So that's not what we did. We analyzed this with 192 measures. And for example, then you get results like this. This is the topology. The nose is here, ears are here. This is patients, and this is controls. And you can see they are not the same. So there is a huge difference between the schizophrenia patients and the controls. This is another one. Here you get qualitative effects. So that's all fine. So if we did this with 192 measures, we found that 69 out of these 192 showed a significant difference between the controls and the patients. So each of these 69 measures tells you something about schizophrenia. And usually what people do is then they say, oh, the alpha band has something to do with the communication between areas and things like this. So we could have written 69 papers. That's quite nice for a student. Unfortunately, Dario got bad boss, me, and said, no 69 papers, only one. And what Dario did is he correlated these 69 measures in the patient population only. Once more, these 69 measures tell you something about a difference between controls and patient, about an abnormality. You would have expected that they correlate with each other. And you can guess what happened? No, they don't. This is another plot, but the pale thing more or less works. And what you can see is there are a few correlations here and here. Some are trivial, maybe a few are meaningful. But in principle, no. Yes, these measures tell you something about schizophrenia, but all of them, or most of them, tell a different story. That means there are at least 69, either there are bad tests here, idiosyncratic tests, I come to this in a minute, or there are 69 factors in schizophrenia, minimum. And if you just break down the variance, now the variance is 100%, and you divide by 69, that means on average, each of these tests explains 1.4% of the variance in the data. That's really nothing. That's a problem. So none of these measures is actually representative for the disease. But that's the opposite what people do. They believe, because they got the significant result, that they just need to find out what's deficient with alpha, what's deficient with beta, and they all believe that they basically have a pointer to the core of the disease. I don't know what, I will come to this, what it means. But at least, I don't know what you think, what we are measuring, but I thought this too. And it just turns out, no, we're not measuring what we think we are measuring. At least I was not measuring what I thought I'm measuring, or something like this. That means these tests are useless. That means all these, I told you it's going to be provocative. And I mean this literally. This is not carnival season, it's Christmas season. I have no presents for you. The point is, the research is wrong. If you basically bet on one paradigm in this type of research, you're lost, unless you're just lucky by accident. Okay, this is message number one. I'm repeating this. The tests are useless. And if you bet on one test, you might run into a big problem. Okay, so I'm running a little bit out of time. This was main message. Now I'm coming to a few messages why this is the case. It's getting a little bit more complicated. Okay, why? So the first point is why not? Actually, you might say, of course, you get no correlations in tests if test-retest reliability is poor. No question about this, yeah. But we have seen that test-retest reliability was quite good, you know, you recall this with these illusions and things like this. So that's not a reason. You might say we don't have power. Come on, with 200 we got power. You might think there is a reliability paradox if you know what it is. It does not apply because we have super large variance. And you might say we used only linear methods. No, we used also non-linear methods. And with topological methods and, we never found anything different. So that's not the problem. I'm not saying that all tests are good. That's not what I'm saying. But at least a few or quite some of these tests were good tests. Next, it could be that these tests are idiosyncratic or that the latent construct does not exist. The first thing is maybe there is not something like visual acuity or something like this. It's just something we have in our mind. And it's a fallacy to believe that just because there are spatial frequency, we can see spatial frequency, there's something in the brain that analyzes spatial frequency. So maybe that is wrong from the beginning. The other thing might be that the test measures something, but it has nothing to do with spatial frequency in the way we think about it. So these were our three tests, you know, this was with the letter S, the Gabor. You can have this with high spatial frequency phases or low spatial frequencies. You can just imagine, for example, you might get a nice difference between low spatial and low and higher spatial frequency grading just by comparing white and black here. This has nothing to do with spatial frequency. It's just something that measures a difference in luminance. Yeah, then you would fail with these tests, for example. So the test measures something, it gives you a nice result, but it has nothing to do with the latent construct. So there might be a latent construct and the tests just don't measure it. Or the latent construct is not there. This is an option, and this potentially is going to happen. So that's something you need to take into account. The other thing is that the assumption of this monofactoriality is wrong. And in particular, significance is not a good guide. And now it's getting a little bit complicated once more. It has nothing to do with the main message. It's more about the intuitions you have about statistics, or at least what I believe about your intuitions about statistics. Let's see how this works. So you might say, hey, you got significant result. You know, this Gabor tells you something about aging. Actually, it doesn't need necessarily be. It could be maybe just older people haven't used mobile phones. So maybe about use of mobile phones or not. But let's assume the test really found out something about aging. So it seems to be that the test is a useful test, like with the schizophrenia patients. And then you can say, yeah, the significance tells us there is something to explain. There is something we want to know. And I will show you with the next slide. No, maybe not. Maybe not. Let's see how this works. So significance is not a good justification for the selection of a test. Okay, small recap. So if you measure, for example, performance in a test between young and old, but we had all before, you know, with the Gabors and all the patient and blah, blah, blah. Let's say we have young and old people. We have the mean here and the standard deviation. And the D prime tells you how well we can discriminate. That's basically what's behind the t-test. Okay, I think you all know this. Just a recap, a D prime of O dot 2 is small, O dot 5 is medium, O dot 8 is large. But large means that the discriminability, say, between young and old, in terms of percent correct, is only 65%, and only if the decision criterion is really optimal. So a large D prime doesn't mean you can discriminate between old and young, just to 65%. A discriminability, perfect discriminability is 4 or something. It's infinity, but let's say 4. And just as a comparison, I think if it comes to body size, male and females, they have a D prime of 1.4. So females are definitely not always smaller than men. But even this has a D prime of 1.4, even such a noisy number. The D primes we have in science are usually smaller than O dot 5. Just to get the context right. Good. So next, what do we do? So we measure data. So where does this mean value come from? Yeah, it comes from individual data with variability noise. So if we do the Gabor task right now, then basically this is the difference between you. So for example, you will have a value in you and they're different. On top of this, there's a little bit of noise. Yeah, that's the idea. So that's the variability among people. And that's a trial by trial noise, which is related for our Gabor test. And by the way, this V is aimed to measure this mechanism in V. That's the idea. Okay. So up to now, we have made inferences about these receptive fields with the help of our Gabor. Let's look at it right now directly through a microscope. And you get a lousy microscope from your grandmother, or the one that you're super envy. I think here you get the super envy type of stuff with 70 magnets that measure some laminate structure and things like this. This is what I mean, yeah? Things that cost millions. So let's do a thought experiment very quickly. So the thought experiment says, aha, you do an experiment, 2 groups do it, or 2 people do it, with a lousy microscope and with the super microscope you got in your cabinet. You got in both cases, you got a significant result. You get a Cohen's d of O dot 8, which is a large sample size, a large effect size, and you got the same sample size. So you're going home, or the teams go home. Which of the teams should open a bottle of champagne? Or which of the teams could open a bottle of champagne? Okay, from the way I'm asking you, you can guess that. That's the interactive part.
The lousy microscope one.
Yeah, sure. But why?
Well, if you can find the effect with the lousy microscope, then it's definitely there.
Almost. It goes in the right direction. Let's look at this step by step. Okay, here's our lousy microscope situation. We got a D prime of O dot 8, which is much, much smaller than 4. But we got a lot of noise. At least we have a large standard deviation. So the idea is now, if we had a better microscope, then the noise would go away. The standard deviation goes down by this. And we see the world as it is, clearly all nicely explained by this factor V. We just need to remove the noise. Yeah, that's the situation we all believe when we use statistic, that there is a hidden effect like in physics. We just cannot see it because there is this bad noise. There's this veil of noise through which we cannot through unless we average. That's the idea. So all is fine, and these guys can go home and hope that this situation is the case. They're in a good situation. Let's look at the ones who got the nice microscope or the 7T scanner. We know from the beginning, by thought experiment, it's so super good, there is no noise. Yeah, that's what the thought experiment is. So this is not there. There's only one factor, there's a large standard deviation which cannot go away because there's no noise. And it explains only 0.8, which is much, much smaller than 4. That means what these guys have found is, yeah, they found an effect, this V, that explains also something, but only to a very, very tiny extent. That means there are hundreds of other factors too. You might say, but it was significant. Yeah, that is significant. But as we all know, like very short, if you have a large sample size, you can get everything significant. That means this is not driven by effect size. This is driven by sample size. That means these guys go home. Of course, they're in a better situation than the guys with a lousy microscope because they know that alcohol is actually bad for your health anyway. And for this reason, but what they have realized is that what they targeted as the key explanation just turned out to be one out of the many potentially very tiny ones. And once more, this is 65% if you have a Cohen's d of 0.8. If you go down to a Cohen's d of 0.5 or something like this, we're talking about 3%, 53 or something like this, 54. Tiny, tiny effects. No champagne. That's the idea. In addition, many, many tests are needed. That's the point. Okay, good. Here are a few conclusions. So when people say a Cohen's d of 0.8 is large, this is true if noise is high. But there's a paradox. If Cohen's d is 0.8 and noise is low, then a Cohen's d of 0.8 is not large. It is actually small. So there is a confusion between noise and variability. And we always believe everything that's not the way as we would like to have it is noise. But it's not noise, it's often variability. And I show you 2 examples in a minute. And this leads to this strange paradox that technically we do everything to remove the noise. We spend millions to get better resolution. That's good in some way because it tells you really what's going on. Noise is not good. I don't want to, Michael said noise is good. No, noise is bad, sure. But the point is if there is no noise, you don't need these good devices. That's the point. So what we do is usually, what people say, they say, oh, you said you have this wonderful device, but I see a Cohen's d of 0.8, and they say, yeah, that's noise. And saying, no, sorry, the noise is not there because you got this super strong thing. So in some way, we want the best machines, the best techniques. But then, if it comes to statistics, we all blame it on the noise, which cannot be there in the first place. That's really paradox. Okay, you got provoked?
Yes, yeah.
Good.
Can I be devil's advocate? Because even in 70
Yeah.
fMRI, there is still a lot of noise inherent in the signal.
Maybe not.
Yeah, but you know,
maybe
pointing it as, oh, there is no noise.
Sure.
Super well, like.
Sure. But you can find out what the noise is by test reliability.
If you take some assumptions, yeah. But what I mean is the fact that we get better.
Okay, so you're happy that you have a 1 million device and still are noisy?
I would want them also.
But that's exactly the paradox. In some way, that's exactly the paradox. In some way, you like noise because you need it to basically get out of the.
No, I am totally with you. I wish there was no noise and then we could hate D of 0.8. But currently, even the best tools are still seem still noisy.
Okay.
So like
then you're in a lucky situation, except for that you're wasting taxpayers' money. Okay, that's fine with me.
It means like there's just still.
Sure. This was a thought experiment. Of course, things just scale. The point is, of course, if you have a little bit of noise, then you get it. You can blame it on the noise, sure. But that shows actually how much people always say they hate noise, but in fact they like noise. If it comes to the explanation, they always come with and say, yeah, Michael, that's noise.
I mean, it depends on the kind of noise also.
No.
Yeah.
This is noise is trial by trial noise, not variability.
But I think you're mostly talking about basically uncorrelated noise.
That's what I'm saying. It's trial
with the task.
Yeah, exactly. Yeah. It's uncorrelated. It's trial by trial noise. That's the point. Yeah. But that's usually what people believe. That's why we're averaging. We're averaging out because we believe it's an uncorrelated trial by trial noise, and then the law of the large number basically applies. That's what I will show you in a minute why this is not true. Just give me.
I'm also not with you, but continue.
Sure, I'm not expecting that you all believe this, right? Anyway, but this is actually the paradox, and that's actually what I just said. You know, if this situation prevails, you cannot average anyway. You can only average if the noise term dominates. But if you have true variability, you kill the signal. And that's what we're doing. And I'm running a little bit out of time. Let's talk about noise. This is EEG. And this is done by Melissa and Simona. And this is a backward masking task. We measure an EEG measure, which is global field power. This is basically the variance, but forget it. The TAR starts at 0, and then we find this N1. And the group average is here, and you get what you usually get. You get an N1 component. That's what people usually find in these type of tasks. These are individual subjects, and you can see this guy indeed has a peak. This one get 2. Here we have a subject with 3. This is actually flat. Actually, we have a better subject that's totally flat. And we have some that ramp up. So we have 5 type of people. The 0 peak, 1, 2, 3, 4, and the super late peak. And what we do is we average because that's noise. And if we had glued the electrodes a little bit different, or if the participant hadn't smoked pot the day before, or whatever, these type of things, we would basically get a clear picture. And that's the reason why we average, right? That's why we have a grand average across trials and participants. Okay, that's how the data look like at T0. That's how they look like 5 years later. And that's how they look like 10 years later. This is not noise, that's variability. We should have never averaged these data. We average these data, we draw a conclusion on the amplitude of the N1. Some of these people don't have an N1. Some have no peak at all. Which of these peaks is it? You know, these people have always 3 peaks, 2 peaks, or 3 peaks. They're a little bit cherry picked, but not too much. It's a little bit hard to quantify this situation, but it shows what prevails is not noise. What prevails is variability. And that basically shows that there are many, many factors at work. And the big question is, what should we average? You know, we should have better stratified the sample, finding out which of the 2 peaks is actually the right one. Finding the peak time, and then we average across the different things. So we have super badly stratified our sample and killed signals and potentially created a false positive. Yeah?
Each colored line a trial in this example?
This is single subjects.
Mm-hmm.
Okay, sorry. These are 6 single subjects out of 200. This is day 1. Then 5 years later, we do the same task with the same participant. And that's how it looks. So this is the same participant, one person, like you.
Yeah.
Measured first time, second time, you got a peak.
Yeah.
This is you.
Yeah.
You got a big peak too.
Yeah.
Here's someone with 2 peaks. Yeah, the amplitudes change a bit. But this is a 2 peak type person. And it's a 2 peak type person even after 5 and 10 years.
But is it just one trial or average?
No, that's average across the rest.
Across trials.
This is a subject that basically does
Yeah.
200 trials or something like
Okay.
that.
Mhm.
Yeah. So that we average across the trials, but not the subject. Sorry. Okay, I missed you. Okay, very last point. I'm running out of time. We look just one last thing. So these are traits of participants, whatever this means. The same is true. We had these illusions. We measured them, and here we measured them across 33 days. And you can see if a subject is strongly, that's a Ponzo illusion. If a subject is strongly, weakly deceived by the illusion, it's always across the whole time. This is a trait of the subject. But the very same subject you can find here, somewhere here. And we measured this 5 years later. And the correlation structure was was still quite the same. So if someone is strong with a Ponzo, the person is strong with a Ponzo also after 5 years. We can quantify this and we get this correlation, but I'm running out of time. So again, this shows this not only the tests are good in terms of test reliability, they're also stable across time. So there are no fluctuations in the participants, neither in the test. There is no noise in the test, and there is no noise in your brain. You're a strong Ponzo person or a weak Ponzo person, and you be this way for the rest of your life. Summary. I think we started off with why do we use one test? It's not always true, but usually because we believe there's one mechanism at work, and similar tests basically lead to correlations and target the same thing. We believe that we just need to look for significance, and everything we see, what's noisy or what doesn't look like it nice in the data is noise. That's the idea, and all of these assumptions are wrong. I told you it's going to be provocative. So there is much less noise than we believe. There's much, much more variability. And I think we need to better stratify our samples. We should look at the data first, then see how we stratify the example, and then we should average, if we want to average at all. And then the use of one test is totally of no avail. We need batteries, but I showed you even these batteries don't correlate. So we need batteries of good tests. Just batteries of poor tests don't help you too much at all. So we're developing this type of criteria for tests and things like this. So we're not that far. You can invite me once more, and I will tell you about this. So this is almost the end. I hope you recall the prologue about the science, the nature. So here's the epilogue. We saw that these studies don't reproduce. And we saw that this has, of course, something to do with the business model, that nature only takes explanation of the XY type. And of course, this provokes people to do things they better should not do. And we know that in a system that's so competitive, this is a problem and things like this. And we complain about this if things don't reproduce. But the problem is in the first place, we should not even expect that there are studies of the XY type. X explains Y type. There are these monofactorial situations are rare. And that's why we should not even believe that they are there. And maybe it's not even the goal. That's the goal of physics, where you can pure materials to the degree that you get these monofactorial things. But I think in the brain, this is simply not the case. So maybe this is actually not the thing we want, actually. And maybe the whole thing is misguided, and not only the few cases or the cases where things don't work out. Okay, thank you very much for your attention.